mentioned, my name is David Hughes. I'm a remote sensing scientist with Oak Ridge National Laboratory. I also list my coworker, Matt McCarthy, on the title slide as well, because part of the work I will discuss is led by him, and the other part of the work is led by me. And we're only a few of the researchers and engineers who work on such topics at our facility, and I'll be attributing those people later in the presentation. I also would like to thank Dr. Wang and ISDE for organizing this talk. So the value one finds in passive satellite retrieval of coastal properties is the scale and standardization at which collections can be made. Recently, very recently, there have been some great advances in edge computing at the satellite. As the remote sensing community drives satellites to collect at higher spatial and spectral resolutions, there still remains a significant value of the drone collection, which can allow us persistence, higher spatial resolution, the ability to customize collection for exactly what's of interest to the researcher, an example being modality. So it's my intention in this talk to offer you examples and lessons learned of work we have conducted in scaling and automation of both satellite and drone research that might profit your specific work. So who am I and where is this work coming from? Very briefly, this is a picture of Oak Ridge National Laboratory, or a large part of it, seen here from UAS. We're located in Oak Ridge, Tennessee, on a very large land preserve. We're the largest in staff of the U.S. Department of Energy Open Science Laboratories. And most notably, we are the home to the first and currently fastest exascale supercomputer in the world called Frontier. So my group sits here where the bullet is denoted on the slide, the remote sensing facility. So we spend a considerable amount of time working on creating automated and accurate remote sensing workflows. The case study that seems to appear more and more is the following listed in bullets 1 through 3. That is to say, the major issues are the overwhelming amount of imagery that you can't in a reasonable amount of time put eyes on to see if it's relevant to what you're doing, your research. So as seen in the green box, I will show you some large-scale derived bathymetry from commercial satellite relevant to coastal monitoring. I'll also show an example of how we use edge computing at the UAS to process imagery by machine learning in support of the disaster assessment community. So these here are a few graphical examples of how we use our computing resources to conduct automated feature extraction of buildings, maritime search and rescue, inherent optical properties of the water column, such as bathymetry. And it's very important to note there is a time and place for supercomputers, but the vast number of us can't rely on access to such for our specific research. And deployable needs really can't leverage this readily. So our silver bullet can't only be to solve problems with bigger machines. We have to think smartly about how to efficiently handle large imagery collections. For anyone who needs to monitor a coastline or a maritime process, understanding an actionable timeline becomes critical. So with regards to research, this might not be of importance initially, but for deployable solutions, it will always be a factor. Our goal is to reduce our time and effort in imagery search, pre-processing, and analysis steps in a few ways. The first such effort is reducing imagery to process only features and areas of usable content. Here you see some of our efforts at pixel-wise cloud detection and masking, cloud shadow detection, and water detection. In addition, in the case of UAS, it is a great benefit to have a capability to reduce content of importance to share out in a constrained communications environment and not have to wait for information at each landing and pulling of the drives or sending the kitchen sink at every detection, the kitchen sink being every high-resolution image. Most, if not all, collections are not made right next to a 5G tower. So we need to attempt to reduce the processing load. For satellite, we do this through the previously mentioned capabilities. Masking and mitigation have considerable benefit, not only in improving statistics for detection algorithms that most definitely rely on image statistics, but also in timings to process. As an aside, what if we wanted to try to recover obscured pixels? Mitigation can be another factor for shadow and haze when we do want or need to determine what can be recovered from lost pixels, so to speak. In this example shown, we see cloud shadow mitigated over a barren terrain. We attempt to recover obscured or atmospherically affected pixels through algorithms based on generative adversarial networks and physics-based modeling. Our objective in such instances is to minimize effect on spectral color content through observed metrics. We typically test with images of thousands by thousands of pixels, typical commercially sized imagery using our latest GPUs. So how this results in a pipeline workflow is seen when we process, for example, the entire country of Ukraine, which is approximately 603 square kilometers, from ingest, very important, from ingest to finished cloud detection in under 200 hours, approximately 6 minutes per image strip, but end to end of which is about 5 seconds per image strip in processing. Some other examples that you can use to focus your research interest and not waste your time on other not interesting things is to use some of these other satellite capabilities for large-scale automated and near-automated extraction, such as one of our developed capabilities is mensurable debris estimation from 2-view satellite epipolar reconstruction. That's at the top of the slide over a building in Oklahoma that was affected by a tornado. As you can see here, it's a way of, at the sensor resolution, developing a mensurable estimate for debris. As well, nighttime lights is very important using NASA input and processing the final product by ORNL. An example here shown of Ukraine as well from previously. But both of these give the capability to show where issues may arise in disaster scenarios or for assessment of coastal regions due to climate-induced events. The example I will show you today regarding edge computing was funded by DOE CSER, standing for Cyber, Energy Security, and Emergency Response, for energy infrastructure assessment. We currently expect such a disaster to be manifest like a hurricane or a tornado, and look to support other varied disaster types in the future. Regarding our work in UAS edge computing, let's get a sense of what components of a drone system we affected with our work. We showed improvements in these various parts of UAS collections: the platform, global command and control, and geopositioning. Whenever delving into such a topic, I highly recommend a multidiscipline team. It's essential. And here I draw your attention at the bottom of the screen to the multidisciplined ORNL team that was essential to develop photogrammetry, UAS, remote sensing, and embedded software for this capability. So we first started out with a custom airframe we called Cornelia. Here you see we did not emphasize time in air, and we spent considerable battery life on our onboard capabilities, such as NVIDIA Jetson Nano processing of our Docker image, wireless and satellite mesh communications, the nature of it being a quadcopter. Our next generation is looking to support fixed-wing UAS, such as the EB, that is showing promise for longer flight times because it's fixed wing and more ground covered as well. We do not have a sophisticated IMU for geopositioning, which could be improved upon, but we wanted to build for the lowest common setup we were seeing from state and local governments, along with the lowest budget. So we build with a 3-band visible camera and commercially available parts. We need to deploy a simple, maintainable solution. To be clear, I'm not advocating that Cornelia that you see here is a simple, maintainable solution, but it is the research frame we chose to investigate and develop such. So using Cornelia, we settled on a web-based control and monitoring system called MAVNet. MAVNet allows all results to be communicated out to stakeholders such as sponsors, analysts, operators, all watching real-time the resulting detections. As you see from the example image in the top right of this slide, one sees the drone collecting imagery and assessing the infrastructure at those points with a thumbnail, and in the thumbnail, the called out object and its status as damaged or undamaged. The bottom image shows the full resolution collected imagery, here from Hurricane Ida in South Louisiana, which due to its size is not provided until landing with burned in object detection for wooden utility poles. The pole locations are not known and are extracted from their spatial and spectral presentation in the imagery by our machine learner on board. Due to the constrained environment the drone is collecting, the drone searches out for available wireless connections, as well as uses satellite-based communications if open wireless is not present in the area, typically the case in a devastated disaster area. Satellite communications considered are from Iridium, outlined here. Due to that seriously constrained pipe, we only send geographic coordinates and a short status message for damage assessment per detection. The ability of MAVNet to allow for mesh network connectivity and beyond line of sight control is a great leap forward in our work. To the right, you see the web-based interface for beyond line of sight control, where one can designate what to collect and reroute as needed from anywhere with an available web interface. Our imagery processing workflow in Cornelia is in 3 stages: collection of imagery, processing of imagery, and uploading of results. Relevant callouts for this workflow are that we currently retrieve geospatial location through an ORNL developed drone to ground model that we built that has no stabilization or gimbal. This is because we are currently seeing sufficient results, but also to lower the bar for anyone to use without a significant financial investment. The processing of imagery was utilizing YOLO V3 and V5 models. So out-of-the-box YOLO models processed on board with the NVIDIA Jetson Nano, as I mentioned, using Python code on a Docker. And the uploaded results we've already mentioned. I won't spend a lot of time on our machine learning deployment, but it's worth mentioning that we did end up going with YOLO object detection models. Work on building new model architectures and hyperparameter optimization are areas ORNL has great expertise in, and we look to invest some time in the future for this capability, especially as we expand our observables and disaster types. To exhibit some comparatives to the right on this slide, here are some examples of different YOLO versions and their qualitative performance for us on our project. To improve assessment and position of observations, we found that multiple observations of poles are useful. So as the UAS tracks through the sky at a set velocity, pointing angle, altitude, set ephemeris, it captures identical observations at least twice, and we aggregate these results as we're looking obliquely. So if one doesn't catch an observation the first time, we'll most likely get it the second time. I mentioned earlier there, geopositioning was not the greatest, as it's working off of the pitch, yaw, roll, and location of the UAS and the pointing of the sensor. As we're viewing obliquely with Cornelia, the distant pixels are disturbed most by jitter and turbulence. The good news for our particular project was that geopositioning is not terribly important as long as you gain causality for damaged infrastructure. For example, this area has many downed poles or no downed poles seen in this area. As you can see from the graph, we're fairly certain when detection is in the bottom third or half of the image. From our deployment, inference speed is very appropriate for our frame rate. Our F1 score is not enviable, agreed, but we know this is because of our growing training set, which we will have seen improvements in as we've increased training data over various locations of hurricanes and tornadoes in the US Southeast. Our take home here is that we can have fast results and don't require a very complex model for our object of interest. We're very interested in collaborating with other UAS collectors, specifically now in the US Southeast. So if you are interested in providing data to our model, please reach out to me and I can share our data requirements document for how to collect imagery that's usable for us. On March 29th through 30th, 2023, a tornadic event occurred in and around Amory, Mississippi. That's in northeast Mississippi. We deployed a team of 2, and these results are what we gain as stakeholders back in Oak Ridge, which is about 350 miles away, over an internet connection. We see from constrained communications the locations of poles and images available to grab from thumbnails. These results are made through the MAVNet interface, showing immediate context and the ability to change flight plans and analysis on the fly. So what you've seen in this first part of my talk is we've had the ability to demonstrate a prototype UAS capable of edge and real-time detection and working with our relationships with state, national, and local entities to actually collect and help current disasters that take place, hurricane and tornadic events. What's next, as I mentioned, is we really do need to investigate these other platforms that have various ways of collecting. Nadir collects as opposed to oblique collects, fixed wing instead of quadcopter, and also, as I mentioned, investigating the building of our own models through different algorithms, genetic algorithms and such, machine learning algorithms, to maybe whittle down that model to what we really need for assessment. Maybe we don't need the out-of-the-box larger model. At ORNL, as elsewhere, drones are expanding their ability to collect processes currently done terrestrially or manually. As Chris DeRolf shows in his ORNL research involving identification of mercury methylation hotspots using drones with LiDAR, we can extend our drone work into areas most relevant for climate change and aquatic environments. we can produce results at larger scales with an eye toward future automation. One area that can benefit from algorithm development that holds up to varied coastal environments and can be produced in an automated fashion is bathymetry. Accurate and up-to-date maps of coastal bathymetry are critical for multiple sectors and applications, such as coastal resource management and urban planning amid accelerating sea level rise. Traditional approaches to mapping bathymetry rely on ship soundings or LiDAR measurements that can become costly, labor-intensive, and time-consuming, most importantly. These methods vary in applicable depth range and accuracy and cost. As a result, approximately 70 to 80% of the global coastal zone lacks accurate bathymetry maps, let alone those of high spatiotemporal resolution. This is a solid target for satellite-based methods that scale and can be automated. As a historical reference, in the early days, when I was but a graduate student in the late 1990s, of coastal optical properties like bathymetry, we investigated the use of hyperspectral imagery, where we learned for bathymetry that we can get very sufficient results from multispectral commercially available data. And having available commercial multispectral satellite data, such as seen here from WorldView 2 and WorldView 3 satellites conducted by Matt McCarthy at ORNL, we chose an area that covers about 3,700 square kilometers, the Florida Keys study area, and examined for a scalable automated bathymetry capability. This particular project, led by Matt McCarthy, required 34 WorldView images, which he required through a government license with the provider. The work was limited to the region from Key Largo to Key West and included both the bay and ocean sides of the island chain. The former is characterized by shallow sandy bottom mixed with seagrasses, while the latter is comprised of deeper sandy and hard bottom between patch and offshore reefs. The diversity that needs to be accounted for is found in the turbidity in the water bodies with varying concentrations of light attenuating particles like chlorophyll. The graph here shows the spectral profiles and spectral variability of water with different chlorophyll concentrations. The discrepancies in blue and green reflectance highlighted here indicate the importance of accurately estimating chlorophyll concentration so it can be corrected for in order to derive an accurate estimate for depth. The method pursued for this work is based on the band ratio approach. Shown here is the natural log of blue band divided by the natural log of green band and refined with coefficients M1 and M0. It is those two coefficients that must be accurately estimated on a scene-by-scene basis to accurately estimate depth in every aquatic pixel throughout the image. So the objective was to develop an automated pipeline that estimates the turbidity in the scene to correct for turbid attenuation, calculate those coefficients automatically, and then use them to map bathymetry across each scene independent of any validation data. The approach followed this long laundry list of processing steps. I won't spent a lot of time going through it, but basically going through radiometric calibration using standard equations, atmospheric correction to correct for Rayleigh scattering, converting to reflectance, sun glint, which would be a completely separate topic, following deglinting equations from Headley et al. 2007, and then really coming to rest in the estimation of water column components. With those estimate of water column components using work from Xuanmin Hu and Zhongping Li to calculate an index representing water column attenuation. This was then converted to chlorophyll concentration estimate, and with that estimate, we can then get at those tuning coefficients, M0 and M1. We then apply the band ratio equation I showed you to every water pixel and produce a raster map wall-to-wall bathymetry. So this is what we get after mapping all the images. We mosaic them together to show a seamless map. And it was validated using NOAA's LiDAR-derived digital topobathymetric models, which are at 1 meter horizontal resolution. These models were created by NOAA, and they coincided with our satellite image collections. A total of 635,081 validation points were used for estimating the accuracy of the resulting bathymetry map. And as you can see here, we're able to calculate the 34 images in 27 minutes for a rate of about 47 seconds per image. Whereas for the LiDAR map, it took 4 months and 85 aerial flights to collect the data that was then processed into the DIM and made available about a year later. As an additional example, I just wanted to show this transect to show the way in which we're mapping very well between the depths, between the LiDAR truth data and the extracted bathymetric model. And to summarize this work, we mapped wall-to-wall bathymetry at 2-meter resolution down to 15 meters, a very effective automated approach with those 34 images at really about over 100 square kilometers per minute would be the rate. I want to thank you so much for your time.